Have you ever just stopped and thought about how absolutely everything in our universe is connected? I mean, from the social networks you're scrolling through every single day, to the massive global supply chains delivering your packages, down to the actual literal neurons firing in your brain right now. We often think of math as just isolated numbers and abstract equations, right? But at its absolute core, math has this highly specific, totally rule-based way of describing these invisible connections that hold our entire world together. So today, we're diving right in. We are unpacking the architecture of these connections in this explainer by looking really closely at the fundamentals of mathematical relations. To keep things manageable, we're breaking this down into 3 logical steps. First, defining mathematical relations. Next, 3 forms of representation. And finally, the essential properties of relations.
Let's jump right into Section 1, defining mathematical relations, the foundation of connections.
Now, mathematical relations honestly shouldn't be intimidating. At their core, a relation R from set A to B is really just a subset of A cross B. That's it. This is the absolute bedrock of everything we're talking about today. Think about it like this. If you have one group of things, let's just call it set A, and a totally different group of things, set B, a relation is simply a specific collection of pairs where one item comes from A and the other comes from B. It's just a subset of all the possible pairings, which we write out as A cross B. What I love about this is how stark and literal mathematics is when it comes to defining connections. It doesn't care about the emotions, the whys, or the how. It just states, hey, here's group A, here's group B, and here's exactly how they map to one another.
Okay, moving right along to Section 2, 3 forms of representation, the blueprints.
So once we have that foundational definition locked in, we can actually view it through 3 completely distinct blueprints. First up, we can look at it as a set of ordered pairs. This is the most direct translation of our definition, literally just a list showing exactly which element in A pairs up with which element in B, treating the whole relation as a simple subset. But what if we need to feed this exact same information into a computer? Well, then we use the second blueprint, matrix form. Here we're basically creating a grid. The rows represent set A, the columns represent set B, and we literally just pop a 1 in there where a connection exists and a 0 where it doesn't. Super clean. Finally, what if we're visual learners? That brings us to the digraph form. And by the way, digraph is just short for directed graph. In this blueprint, the elements themselves become nodes, just dots on a page, and the relations become the edges. Those are literal arrows drawn between the dots showing exactly how they connect. It is honestly pretty fascinating how a single core relationship translates so seamlessly across simple listed pairs, grid-like matrices, and visual digraphs. So the really crucial takeaway here is this: same architecture, 3 different lenses. Mathematics doesn't really care about your feelings, it just cares which blueprint you're using to look at these subsets. Whether you're listing out pairs, mapping an entire grid, or drawing arrows all over a whiteboard, you are describing the exact same underlying reality. You're just picking the lens that best solves the specific problem right in front of you.
Which brings us to Section 3, Essential Properties of Relations, the Physics of Connections.
All right, we've mapped out exactly how to draw these connections. But now we need the rules of engagement. First up is the reflexive property. The pair A, A is an element of R for all A and set A. Now, what does that actually mean in plain English? It just means that every single item in the set connects back to itself. Think of a web page that actually has a link pointing right back to its own homepage. That is a reflexive relationship. It's the absolute fundamental rule for self-connection. And here's the kicker. If even just one single element in that entire set doesn't point back to itself, the relation as a whole cannot be called reflexive. It's all or nothing.
Building right on top of that, we have the symmetric property. This one states, if the pair A, B is an element of R, then the pair B, A is also an element of R. I love this one because it brilliantly illustrates a perfect two-way street of connection between different elements in our set. Basically, if element A points to element B, then B absolutely must point back to A. Think about a friendship on a social media platform. If you're friends with someone on there, they are automatically friends with you, right? The connection goes both ways. That is exactly what a symmetric relation looks like in action.
And that brings us to our third essential property, transitive. This one says if A, B is in R and B, C is in R, then A, C must be in R. This property is incredibly powerful, mainly because it shows exactly how a chain reaction of connections is mathematically formalized. It's essentially the friend of a friend rule. If node A connects to node B, and node B connects to node C, well, a transitive relation guarantees there's a direct express line from A straight over to C. Without this specific property, things like logistical routing or even tracking your ancestry would be completely impossible to map mathematically.
Now, contrasting these two properties really reveals how the rules of the game start to escalate in complexity. Look at item 1, the symmetric property. It's really just a simple swap. A to B means B to A. It's just a mirror. But then you look at item 2, the transitive property, and that builds an entire three-part logical chain. It requires three totally distinct variables, A, B, and C, to interact in a highly specific sequence. Comparing them side by side like this shows us how mathematical relations can scale all the way from a simple handshake between two people up to these incredibly complex, multi-layered networks where influence just cascades right down the line.
So you might be asking yourself, why does all of this actually matter? Well, it matters because these foundational rules map our incredibly complex world. We started out with a really dry definition, right? A relation just being a subset of A cross B. But when you apply these representations, the ordered pairs, the matrices, the digraphs, and you start enforcing these properties, reflexive, symmetric, transitive, you suddenly have the exact tools you need to explain massive, real-world networks. I mean, this exact math is literally what sits inside the algorithms predicting your next online purchase. It's mapping the most efficient flight paths around the globe. It's even modeling how information, or a viral meme, spreads through entire populations. Which leaves us with this final, kind of provocative question to ponder. What hidden relations and digraphs are secretly architecting your digital life right now? Literally every single time you click, like, or subscribe, you are becoming a node in a massive mathematical set. You're creating an ordered pair with a piece of content. Are those connections symmetric? Are they transitive? This invisible architecture is absolutely all around you, constantly being written into matrices behind the scenes. Keep that in mind the next time you log on. Thanks so much for joining me for this explainer, and keep questioning the connections around you.